Hey, welcome back, everybody. Well, this is our next video where we're going to look into batch normalization. But just before we do that, let's take 5-10 minutes and go over a review of what we've done so far. In the last couple of videos, we've been going over what's called batch gradient descent and mini batch gradient descent. And what we had was a network that looked kind of like this, where we had our inputs were the X table. We had a lookup table I called C. And X and C, we combined them together to form an embedded table, E. And then we used the weights and the biases, weights 1 and bias 1, to generate our hidden layer neurons. Then we activated those neurons using the tanh function, which gave us this Z table. And then of course we used the bias 2 and weights number 2 to generate our predicted values of Y. Notice also that these are all, because we're dealing with the mini batch, these are all basically 32 rows. Like, so if our hidden layer H was, let's say, 100 neurons, it's really 32 by 100. And if our predicted values are just 27 neurons, they're really 32 by 27, because we're dealing with a mini batch. Okay, so we've done that. And I just wrote down some of the, not real definitions, but just kind of a sentence that kind of explains a little bit about what these terms are that we've used so far. Lookup table, it maps the target values of the labels to n-dimensional vectors. For me, anyway, since I'm learning as I'm doing this is all starting to make sense. I hope it is for you too. Embeddings are numerical representations of real-world objects. Hidden layer is a layer of neurons that is neither the input nor the output layer. So it's some hidden layer is some layer in between the inputs and outputs. Weights and biases are neural network parameters. Activation is a function that calculates the output of the node based on its individual inputs, and in our case we're using tanh here as our activation function. Softmax function turns a vector of k real values into a vector of k real values that sum to 1. So basically what we're doing is, with softmax, we produce a probability distribution. So values from 0 to 1 for all the different items. We also looked at the cross entropy function. It's basically a loss function used in machine learning to measure the performance of your model, and it uses negative log likelihood. Okay, so that's how we measure our loss. And for gradient descent for mini batch, I just put up these formulas here. So for back propagation, we just go through with a loss here, loss with respect to our predicted values, loss with respect to bias 2, loss with respect to weight 2, loss with respect to bias 1, loss with respect to weight 1, and the loss with respect to our embedded table. And of course, once we work out the loss with respect to our embedded table, we can then unembed those gradients into a into our lookup table gradients, so that our lookup table can then be updated properly. And what else do we have here? Oh, I also have, what I didn't show you last time was a plot of our loss. What I did here was basically all I did was, I think in one of my C programs, I just put in a print statement to print out the loss. So I ended up with this loss, this little file here. So you can see the loss started out at 4.194136, and it just, the loss kept getting better and better. So how many of these values do we have? 200,000. So this loop went through 200,000 times. If I go plot, and I just plot the loss, you can see what it kind of looks like here. And if you use your imagination, you can probably see that the loss is kind of going down a little bit. You know, so this is after 200,000 iterations, but you can, you know, I guess you have to kind of look really, really closely. You can definitely see that there's a kind of a slope, a downward slope, to indicate that the loss is improving. Okay, so that's basically a review of what we've done so far in the previous videos. And what we want to do now, let me get rid of this thing. What we want to do now is go on to start talking about batch normalization. Of course, so I've written down here some things I found on the web, probably from Wikipedia or something. It says batch normalization, a method used to make training of neural networks faster and more stable. So that's really, I guess, what the purpose of normalization is to make the training faster and more stable. So you get better results, I guess. And this was all proposed by these two researchers back in 2015. So for batch normalization, we need to kind of review a little bit about basic statistics. And we have to look at what is mean. Mean is just the average of a given set of data. Variance is the sum of the squares of the difference between all the numbers and the means. And the standard deviation is the square of the variance. It's a measure of the extent to which data varies from the mean. Okay. And so for mean, variance, and standard deviation, I put together a little PDF here, a little bit too big. But you can see that the mean is just the sum of all the values divided by the number of values. Of course, the variance here says just the sum of the squares of the differences between all numbers and the mean. So this is where you have the sum of the squares between all the numbers and the means. And of course, the standard deviation is the square root of the variance right here. And we have this little epsilon in here just to make sure that we don't end up with a square root of 0, which could end up with giving us problems. So Okay, so what we're going to have to do now is we're going to have to go through and update the hidden layer. So let's take a look at what I've got here. Open another 2B here. Guess I don't need this one anymore. But to update the hidden layer, to normalize, you could say to normalize the hidden layer, this is the two formulas we're going to use for normalization. So let's say HO here is our hidden layer. If we take every value well, this is our original layer, I guess, or hidden layer, minus the mean, and divide that by the standard deviation, then we get we can say that that's been normalized. So it looks fairly simple to do this operation, and I guess it sort of is, I guess. But anyway, the second part of the normalization is to introduce two other parameters. This gamma parameter here is basically used to as a gain, or to increase the gain of the normalized layer, I guess you could say. And beta here is kind of used, I guess, to shift it a bit. Let's see if I can kind of draw out my own impression of that. I mean, again, I'm not an expert. I'm learning just like you people are. But if I go to here, let's say that we just have a, if we have something like this, a distribution like this. So we have some kind of distribution like that. Well, the parameter, gamma parameter, is basically multiplied by the or the normalized layer. But so I think what it does, I could be wrong here, but I think what it does, the gain, it makes it bigger, so it might make it like that, more kind of steeper or something. I'm not sure, something like that. Whereas the shift beta can kind of move it over. So if you have it like this, I'm not sure if it moved it over a little bit to one side or something. So I get, this is my own personal impression. I mean, I could be 100% wrong here, but I think that's what's happening here. Now, let's see, how do I get rid of this discard? Whenever they do batch normalization, they always include this extra piece here to kind of change the gain and shift the distribution around a bit. And we'll be doing that in our code as well. So basically down here, if you look at gamma, scale, and shift beta are just two more parameters. So they're like, you can treat these like weights and biases, this gamma and beta as weights and biases, because we're going to have to find during backpropagation, we're going to have to find their gradients to update those two parameters. All right, so let's move on to some code now. Let me close this, and we'll go to some code. Now, the first thing you'll notice is that I'm switching over from using Vi into VS Code. And the reason is that the code just started to get a little bit too big for just one file. So what I did is I split it all up into a lot of C files or C programs and some header files. So maybe what I'll do first is just go over the code. And by the way, all of this, like I said before, I have all of this on my GitHub, so you can easily download it. But anyway, let's take a look at some of the C programs I have here. I'm looking right now at my main here, but I also have, for example, I have here back my code for doing the back pass or the back propagation. I also have a forward pass, my code for doing the forward pass. I have a helpers file here that just has just general kind of functions I need for the program. Of course, I have my main C program here. I also have a matrix C program here that has all kinds of matrix functions here that I use. All kind of handwritten stuff. And I also have normalize. This is all the functions I need to do the normalization. I have another C program here called printers, which allows me to print things out. This function will print an integer array, or this one will just print a regular array. This prints an array in E format. So I have lots of different functions here printing out bigrams. So these little functions were to help me basically to debug and find errors in my code. And then finally, the last C program I have is testing.c. And this is where I use MakeMore to create more names. And I also have a function here for split loss. This is where I split all the data into 3 chunks, which I think I went over. You know, the training section, the development section, and the testing section. And I think those are the only functions I have in this part. Okay, so why don't we go, we're going to just talk about the forward pass now. And let's start with the Python program, which I have here. So we went over a lot of this Python program before. I haven't changed much, except I've introduced normalization. So again, you can see we import torch. I also use NumPy a little bit in a few places. So, and I'm also using again the C library for generating my inputs, which are the bigrams. And I also use PyGSL, GNU Scientific Library, for generating all my parameters here. Actually, in this code here, yeah, I also have alpha or gamma and beta somewhere, which I don't think they're random to start with. I think they're just ones and zeros or something like that. I set print options here. I want precision to be 5, so I set that up. Just get 5 decimal numbers. Here's my make random function for making my random parameters, which are C, W1, B1, W2, B2. And again, I'm just using the GNU scientific library to do these random numbers here. This build data set, this is directly from Andrej's code, basically used to split the data set into 3 chunks. Then again, we go through just like we did before. We have these 2 functions, string to integer and integer to string. I set my block size here to 3. There's another parameter I introduced here called momentum. We'll talk about that a little bit later. What else? So here are our 3 data sets: X training, X development, and X testing. And Y training, Y development, Y testing. And so I go through and I make all of these tables here. And you notice for the gain and the like gamma and beta, which is gain and bias, I call them here. The gain is just set to 1s, and the beta, the shifting parameters, is set to 0s. And I also introduce here another variable called the running mean and the running variance here. And I just set them all basically to 0s. Well, why do we need the running mean and the running variance? Well, see, as we go through the training session, which 200,000 loops, 200,000 iterations, the mean and variance in our normalized layer keep changing as we go through. We keep renormalizing the normalization layer, and so what we do is we just keep track of the running of the mean and the variance, so that we can use those when in the end when we want to make some new names. Because when we're making new names, there's really no way we can calculate the mean and the variance during that part. So we kind of have a mean and a variance that we save during the iterations, during the training, and then we use those during the actual production of new names. Okay, going further down, we have our parameters. Now you can see our parameters include the gain and shifting, or the gain and the bias, gamma and beta. Okay, so that'll tell us. And our learning rate 2 is going to be 0.1 to start with, or minus 0.1. So now we go into our main loop here on line 75. We're going to do 200,000 iterations here. We're going to change our learning rate halfway through. We're going to decrease it by a factor of 10. And the first thing we do is we get a mini batch. So we're going to get 32 bigrams here. And again, I'm using the random number generator from the C library to do this. And then I start the forward pass by creating the embedded layer. HO is my original hidden layer, which is the embedded layer times W1 plus B1. And I put in this line here just to retain the hidden layer gradient. I don't really need that, so I'll just comment that out. And now here's the line 89 where I do the normalization. And the normalization just means you take the original neurons and you subtract the mean divided by the standard deviation. And this is all done by PyTorch, more or less. I don't want to say auto-magically or automatically. And here's where we keep track of the running mean, and here's where that momentum comes in. Remember, one of the new parameters I introduced up here was the momentum was 0.1. So you can see down here, so the running mean is just going to be 1 minus the momentum times the running mean, plus, I guess I could go here. Let me make this window a little bit bigger here. Plus the momentum times the running mean of the original neurons, HO. And the running variance is the same kind of thing. And again, we're only keeping track of these two values just so we can use them when we're producing more names. Then we activate, so I can say HA is our activated neurons by using tanh. And you notice at the same time as we do the activation, we're also introducing these, the gain and the bias. So the gain times the normalized layer plus the bias or the shifting, the beta. And then our logits comes out to HA times W2 plus B2. And our probabilities, we use softmax. And our loss, we use cross entropy. Okay. And then we go in and we print out our loss here. And then we do the backward pass. Well, we can set all of our parameters here to none. And I don't need this one here either anymore. So I can just comment that guy out. And I don't want to stop it here. I want to let it go. So let me, actually, why don't I just delete these lines? I don't really need them. Yeah, let me get rid of all these lines here. They're just interfering here. Okay. So we go through this loop, and you see the backward loss just does everything automatically for us. And then for our parameters, remember our parameters, how many parameters do we have now? Where did I see them here? Right here we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. We have 7 parameters. So in the for the update, we go through all 7 parameters, updating the gradients, updating the parameters using the gradients, their own gradients. And once we're done this loop of 200,000, then we can produce the loss for the full training set. The loss for the full training set. And we can also produce the loss here for the full development set. And once we produce those two losses, we could then go into this MakeMore names. And this is where we end up using the running mean and the running variance to compute the normalization layer. Okay, so the normalization layer here is just H minus running mean divided by running variance. And then we can say Hn is equal to tan H. And again, our gain and our bias here are used. And we then compute the logits, probabilities. And then, of course, I switch over into my own well, not mine, but this multinomial function from the GNU Scientific Library. And we print out some of the answers here. Now, if I was to do this, let me save this guy here. Save all, and I can just go here. And I can run this guy. Let's see if it... And you can see the number of parameters are 12,297. That's really the sum of all of the data in those seven different tables that we're using. So we can go through that, and while we're doing that, I just want to move over to here, and you can see that in my main loop in my C program, I do something very, very similar to what we've been doing in the Python program. I have a loop here of 200,000. I get a mini batch here. I embed the mini batch into the embedded table. I generate the hidden layer. HO is the hidden layer. It's just basically the embedded table times W1 plus B1. And then I do the normalization here. So I end up here in this function to do the normalization. And what I did here in this line 128 was I ended up just copying the normalized layer to H. So I could just, so from this point on, H is the normalized layer, but I've also saved it here before the gain and the BIOS were done. Okay. And then I do the activation. I get the logits. I compute the loss with cross entropy, and then I can start my back propagation. Okay, so I won't bother with that. I'm going to do back propagation is going to be the next topic here. But let's just let me go through here. Oh, I also did I guess I can show you that. I put together a make file here to make my life a little bit easier, so I can and I want to run my own stuff. I can do that, and then I can say make, and it builds everything up for me in one line, and I can run it. I don't know if I have it set up right, but you can see that mine has also 12,297, and if I compare that to the Python program, 12,297, but you see the first loss 4.3168 or 868, 4.31868, but you notice the second loss after 10,000 iterations, I have 2.43, and here in the Python they have 2.40. So this is the first time now where my answers are not lining up properly with the Python program. And there is a reason for that, and I will probably explain that when I start talking about backpropagation. In the meantime, let's look at some of the answers from the Python program. You can see that the training loss was 2.06 and the development loss 2.11. You can see some of the names, not too bad. Matra or Zarla, Leia, Darius, Roya. So some names are not too bad. Lena, ham, ham, okay, I don't know. Daily. So some names are not too bad coming out of the Python program. I guess I can also probably, I don't know if there's anything else I can show here at this point while we're waiting. No, probably nothing else I can show here. So let's just go back through some of the code. Let's take a look at one thing I want to show you, which I'll talk about later, but in my matrix file here. In my matrix file here, I've got some functions here that add up a column of floating point numbers. Like, for example, this function here, I have that adds up some floating point numbers. You have a column here, m of floats, and the length of those floats, and it will add up those floats, and it will return the sum of those floats. I also have here another function, a little more complicated, that also adds up a column of floats and returns the sum here of the floats. Here's another one that will add up a column of floats and return the sum. Here's another one that adds up a column of numbers and returns a sum. And this is the way, by the way, that NumPy adds up floats. It does it by what's called pairwise summation. It's a recursive little algorithm. And this is the one I use whenever I want to add up some numbers. And this is, by the way, where my system deviates from the Python program. Now, going back to the answers I got, some of them, if you look at the loss for the train, I got 2.1, whereas the Python got 2.06. For the development, I got 2.15, and the Python got 2.11. And some of the names I got, I guess, not bad. I mean, Van, Dawn, well, Dawn is actually a name. Jackie with a Y. Is it Zaja? Harm is a name, I don't know. Kazar, Joy Lee, Kenmi, Blonde, Joza. So here's one, Lucky with an I, or Arova. So I guess the names I'm coming up with are, I mean, you can't really say they're any worse than the Python names. I think they're probably both or equally valid new names. Anyway, so I want to just close all this stuff now. Let's see, close this. And what I want to do now is I want to go back and I want to start looking at backpropagation through the normalized layer. Okay, let's start looking a little bit deeper at the code for batch normalization. We'll start here in the main loop, which I have here. Get mini batch, do the embedding, generate the neurons for the hidden layer, add the BIOS, and then we get to this function called normalize, line 126. So let's see how we do that. If I go to normalize C program here, we'll see we have this function here called normalize. And normalize is basically two parts to it. One part is used for testing purposes, and the other part is used for training. So this else part is for training. And we say for each value in HO, that's that hidden layer, the first linear layer, I guess, we subtract the mean and divide by the standard deviation. And note, standard deviation is the square root of the variance. So xi minus mean over standard deviation. So what we have to do is we have to get the mean here, and we also want to update the running mean. And remember, I think I talked about that just a bit back. The running mean and the running variance are used during the generation of new names. This code here from line 65 all the way down to line 72 is what we use to get the running mean and the running variance. And we just basically save those two values, or the two vectors basically, so that we can use them once we need to generate some more new names. So after we get the mean, we get the variance, we get the standard deviation, and then we get normal here. So let's look at some of these other functions like get mean, get variance, get standard deviation, get normal. I have them all here. Let's go right to the very top. Get mean, compute the mean of each column of a table, basically. And what it does is you can see that what it does, it just returns a vector of the array, which is a summation of the columns. And get mean 1, this function is different from get mean, because what it does is it returns an array, basically batch sized by hidden nodes. So it's getting the mean of every value in a table. And then we have a function here called get variance. Compute the variance, sigma squared, x mean minus mean squared. And here's the code for that in this line 31, basically. And the interesting point here is that when we want to find the average, we divide by the batch size minus 1. In other words, normally when you think of the average, you think of, let's say I had 10 values and I want to find the average of the 10 values. I add up the 10 values and I divide by 10. Well, in this case, if we had 10 values, we're going to add up the 10 values and we're going to divide by 9. And why do we do that? Well, that's that Bessel's correction. If I look that up somewhere, let me just check that. Let's see. In Wikipedia, this is what it says about Bessel's correction. In statistics, Bessel's correction is used in the use of n minus 1 instead of n in the formula for sample variance and sample standard deviation, where n is the number of observations. So we use 1 less than the number of observations. This method corrects the bias in the estimation of the population variance. It also partially corrects the bias in the estimation of the population standard deviation. However, the correction often increases the mean squared error in these estimations. This technique was named after Frederick Bessel. So that's why we have this. Instead of dividing by n, we're dividing by n minus 1 here. To get the standard deviation, we just need the square root of the variance. And here we're adding epsilon here, but I've set epsilon here to 0. In fact, we can take a look at this point of all my parameters. Let me see, where do I have that? Parameters. Right here. These are all the parameters I'm using. Block size is 3, batch size 32, dimensions 10. The in nodes, the input nodes are block size times dimensions. Out nodes are 27, bias vectors 27. The hidden nodes are 200. Bias 1 is 200. Length of alpha is 27. The initial learning rate is set to 0.1. The momentum is set to 0.1. For just after normalization, we used the gain and the bias, these two vectors of 200 each, and epsilon I just set to 0. So if I go back to normalize, so then finally we get this function here, get normal. Okay, normalize HO giving HN. So we started out with this array here called HO, which is like our first linear layer basically, and we end up getting HN, which is the normalized layer. And that's how I did it. Anyway, it seems to work properly. If I go back to the main here, you can see after normalization, what I did was I copied the normalized layer into H here, just so I could use H all the way, the rest of the way down the doing the forward pass. And I also save HN for later use. And then we do our logits, and we did our cross entropy to get the loss, and then we start the back propagation. The back propagation is very complicated for C because we have to do all of the we have to get all of the derivatives ourselves. We have to figure them all out one by one. So in here you can see I get, well, I think it's best if I just go over some of the math I did to work this out. And that would be in, where would that be? That would be right here. Okay, so this is what we got. Why don't I just close this other window here, and I'll just maximize this one. Let's start at the very beginning here, and let's see if I can go through this to make sense. I want to start this too. Okay, so I'm going to use my little laser pointer here, see how well this works. Okay, so this is a big picture of batch normalization. So we start off with our lookup table. We have our mini batch here of our inputs, X. And together we combine these into an embedded table. And this embedded table now becomes our input. And you can see that our first layer here, HO, is W1 times E plus B1. And that's how we generate this first layer here. And then we go to our normalization, and our normalized layer is basically HN is equal to HO minus mu over sigma. This part here, that's how we get from this guy to this guy. And then we do the scale and shifting. Okay, so HN is equal to, we do the scale times HN plus shift. Okay, so we get to this. And then we get to and then we activate this guy using tan H. So we get HA. And then finally, we can get our predicted values by using this formula, Y predicted is W2 times HA plus B2. So this is, and then of course the other thing you have to remember is all of these arrays here, or these tables, are all mini batches, so they're all each of size 32 rows. So when you look at like this Y predicted, which was 27 27 items here, or 27 predicted values, it's really 32 rows by 27, and this would be 32 by like 100 or 200, however number of columns we had. Okay, so those are the formulas we used to do our forward propagation. So let's go and see how that works. So again, we start with the lookup table, C, batch size. I'm just putting in some numbers here. Initially, the lookup table is random. We have a batch size of 32, length of the alphabet is 27, and we create the embedded table. So the embedded table is going to be, if the dimensions were 2 and the block size is 3, then the embedded table will be 32 by 6, 2 times 3. So E will now be our inputs to the network. And I give you an example here of how we generate E. We just go through the X table one at a time. The 5 here tells us which row to go to. We pull that row out and we put it into the embedded table. We go to the next X, which is 3. We go to row 3. We pull out row 3 and we put it into the next available slot on the embedded table. Okay, so you can think of it filled with the vectors from C. Think of each row as a 2D vector because we're using 2Ds, so each one is a like XY vector you can think of. In the examples that I'm doing later, like we're using 10 dimensions, so this is really 10 by 27. Okay. So we start our forward pass. So let's say we had 100 hidden neurons, HO. So we end up with multiplying HO equals W1 times E plus B1. So we end up with this kind of pictorial view here. And we end up with HO, which is like 32 by 100 after we do that multiplication and addition. Okay. So now that we have HO computed from this formula, we now want to normalize it. So we want to normalize the entire batch. So after normalization, the values in the hidden layer will have a mean of 0 and a standard deviation of 1. Okay. So here's the formulas we're going to use. The normalization is the original minus the mean over the standard deviation. The mean here formula is just a summation of all the HO elements. The variance is, and again we're using that Bessel's correction to get the variance, so it's 1, 2, and minus 1 of this squared value here. And then our normal values will be HO minus mu over, the square root of that is just going to be the standard deviation, because I set, normally you could set epsilon here to 10 to the minus 5 to avoid dividing by 0 in case you end up with a 0 in here. But I've set epsilon, in my code I've set epsilon to 0. So we calculate the mean here. So there's the formula for the mean, and I went through the C code a little bit to show you that. Then we calculate the variance of the batch. So subtract the mean from each row of the batch, and square the result. Then we add the columns and divide by batch size. So we end up using, again, this formula here to complete the normalization. So there's how we complete the normalization. And we multiply each row by 1 over the standard deviation. That's if epsilon is 0, of course. And after we do the normalization here, then we have to do the scaling and shifting. It says not actually needed for batch normalization, but is used in most cases. This allows the normalized values mean to be 0 and the variance to be 1. So there's the formula here. So after we do the normalization, we can scale here using the gamma vector, and we can shift using the beta vector. So usually scale, sometimes they call it gain, and shift, sometimes they call it bias. Of course, that bias confuses with B1 and B2, which are the other biases, so be careful about that. In our case, both gamma and beta are vectors of 100 length. That's fine. And we also set gamma to all 1s and beta to all 0s for initialization. We can now implement the activation function. So in our case, it's tan H. So H activated, HA, is just going to be tan H of HZ. And HZ is the array of that has been scaled and shifted. Finally, we compute the last linear layer of our network, which are the logits, by using W2 times HA plus B2, and we end up with this 32 by 27 logits right here. Then we use softmax to convert the log counts to probabilities. So this guy here, we can change them to probabilities so that each row should sum to 1. And then finally, we can then start backward propagation. And this is where I guess it gets to be even more complicated in C, because we have to do all the dirty work ourselves. So the first thing we need to do is to determine the loss with respect to our predicted outputs, DL, dy, y predicted. So the formula here, I say loss is 1/2 y predicted minus y squared. And if you differentiate that, DL, dy predicted, you end up with this over here. Basically just y predicted minus y is what we get. So that's fairly easy to compute because we know that, for example, the probabilities here are real numbers. We have 32 of them in our batch, and they're all real numbers in here. Each row here will sum up to 1. But here in our labels, each row also sums up to 1, but basically they're all zeros except there's a 1, 1 in one of the columns that actually indicates the actual value we're looking for, or the label. So now we have DL, dy predicted. So we've just computed that by doing this summation here. But now we need to get all of the following here. Well, look at what we still need. We need to get the loss with respect to B2, the loss with respect to W2. We need the loss with respect to beta, the loss with respect to gamma, the loss with respect to B1, with respect to W1, and with respect to C, our lookup table. And all of these 1, 2, 3, 4, 5, 6, 7 gradient tables, these deltas will be used to update B2, W2, beta, gamma, B1, W1, and C. And once we do that update, we've basically done one pass through our our loop. But, and here's where it gets even more complex. In order to compute these gradients up here, we're also going to need several intermediate derivatives. So for example, we're going to need to compute the loss with respect to the normalized layer. We're going to need to compute the loss with respect to the variance. We're going to need to compute the loss with respect to the mean, and we're also going to need the loss with respect to our first linear layer. So let's start. We'll start with the easy one, which is loss with respect to bias 2. Well, there's the formula. Our predicted values are W2 times HA plus B2. So if you take the derivative dl dB2, dl dB2 is, by the chain rule, is going to be dl dy predicted times dy predicted dB2. And you notice that the dy predicted cancels out here, so you end up with the loss with respect to B2. And so that's just going to be all this summation, which is dl dy, which we did just a few minutes ago, times 1. Because dy dB2 is just 1. Okay, so dy dB2 is just 1. And similarly, for the loss with respect to W2, we say dl dy prime, or dy prime over dW2 is just, excuse me, is just going to be basically what we had before. This is dy or dl dy, this part here, times HA. Because if you look at HA, dy dW2 here is just going to be HA after we do the derivative. And you notice when we do the multiplication here, I think I need a drink of water. We need to transpose HA in order to do the multiplication properly. Next, we have to get the derivative of the loss with respect to beta. Well, we have HA is equal to tan H of HZ. And we know that Y prime is W2 HA plus B2. And HZ is equal to gamma. You know, I'm going to have to just pause this. Hang on a second. Okay, so I had to take a little stop here. I hope I didn't mess it up too much, but anyway, we're working now with the loss with respect to beta. So in order to do the loss with respect to beta, we need to get the loss with respect to Y prime, the loss with respect to HA, which is W2. We need DHA DZ. Now this is the derivative of tan H. And the derivative of tan H is 1 minus tan squared H. Okay, so you can just look that up, I guess, if you want. And the derivative of HZ with respect to beta is just 1. Okay, so that's how we end up getting this loss with respect to beta. And you can see in the chain rule here, this cancels out here, this cancels out here, this cancels out here. We end up with loss with respect to beta. Okay, so now we need the loss with respect to gamma. Well, it's identical to the loss with respect to beta, except this last term, instead of being DHZ d beta, we need DHZ d alpha, or gamma rather. And that just becomes HN, the normalized layer. And that's why I was saving in the code. I showed you why I saved the normalized layer in my C program. But now we have to go further, and we have to find these other derivatives that are necessary. We need the loss with respect to the normalized layer, which is the loss with respect to predicted values, the predicted values with respect to the activated values, the activated values with respect to the pre-activated values, and the pre-activated values with respect to the normalized layer, which in this one here is just gamma. If you look at DHZ, DHN, see HZ with respect to DHN is just gamma right here. Okay. So that's how we get DHN. Well, we know DL, DHN here, so we want to compute DL, d sigma squared, which is the loss with respect to the variance. And that's equal to DL, DHN, which we just computed here, and DHN with respect to the variance. Now this one here is really tricky to get. I kind of had to look it up, and I watched a lot of YouTube videos to get it. But anyway, this guy, if you look at HN, is equal to HO minus mu over the square root of sigma squared. If you're looking at the derivative of HN with respect to sigma squared in this formula here, this is what you get. This is the actual derivative. Okay? And you can look that up, or you can work it out. If your calculus is better than mine, you can just figure it out. But that's what it comes out to. Then we also need, so that gives us the loss with respect to the variance, but we also need the loss with respect to the mean, and that's going to be these two components here. The loss with respect to HN, and the HN with respect to mu, which is this guy here. That's the, because if you look at HN, where is it here? See, HN, if you look at the derivative with respect to mu, DHN d mu, DHN d mu, that's what it comes out to, minus 1 over square root of sigma squared plus E. And then we also need, well, we already have this loss with respect to the variance, which is computed up here. We need this piece here, which is the variance with respect to mu. So if you look at the formula for variance, this is the formula for variance. So we get, if we take the derivative of variance with respect to mu in this formula here, we'll end up with this answer right here. That'll be the derivative. Okay. And then we need to get DL, DHO, which is the loss with respect to our first linear layer from the very, very beginning of the forward pass. And that becomes 3 different components all added up. DL, DHN, DHN, DHO, which is this guy here. DL, D sigma squared, DHO, which is this is the derivative there. And DL, D mu, DHO, it's 1 over that, which comes from this formula here. Okay, so now we have all of that. So DL, DHO, remember, this is the loss with respect to the very first layer. So it comes out to this times this plus this times this plus this times this. So it's 3 different components. And now we can work out the loss with respect to B1. So that's very simple, because all of the work was done getting the loss with respect to HO, which is this guy here. And HO with respect to B1, well, HO equals, it's just going to be a 1. The derivative of HO with respect to B1 is just going to be a 1. Okay. And then finally, we can get the loss with respect to W1, which is going to be, again, DL, DHO, which we've done up here, all the heavy lifting. And DHO, DW1 from here is just going to be E, right here. DHO, DW1 is going to be E. And then DL, DE is going to be DL DHO. Again, we have DL DHO times DHO DE, which is W1. And now that we can use the gradient of E to unembed that gradient into a C gradient. And that will give us the C gradient, D loss or DLDC. And we're done. And then we can proceed to update C, W1, B1, W2, B2, gamma and beta. And that'll complete the whole loop. Wow, if that didn't hurt, then nothing will. Anyway, let's go back now to look a little bit at the code here. Control C. Go back and look at the code. So if you look at our backpropagation here, you'll notice that we go through and I get that DL, dy predicted. I get the B2 grads, W2 grads, and this is the gradient of the activation, which is basically, remember the derivative of tan H is 1 minus tan squared H. Then I need to do a transpose here of W2, and I get DL DH. So this is the derivative with respect to the, I think the normalized layer. And then DL dz is the derivative with respect to the, is that with respect to the activated layer. So you notice again, I think I mentioned this earlier, I'm using two different multiplications here. Mult AB, which is a standard matrix multiplication. And then I'm also doing A times B, this function I wrote, which just does element-wise multiplication, which I think I mentioned was like A11 times B11 equals C11, and so on. And then we get the bias grad. So see how we're moving backwards through the network. We get the bias grads, which are basically the shift, the beta grads. We get the gain grads, which is the gamma. And then we get the loss with respect to the normalized layer. And then we have to compute these, the mean and there's two different means. One is the mean as a vector and one is the mean as an array. And again, we multiply to get M here. And we go through lots of intermediate steps here. You can see there's all kinds here because I have to calculate the loss with respect to the variance here. I need to calculate the loss with respect to the mean. So I go through all kinds of crazy, I don't know what you call it, twists and turns, almost like a pretzel, I guess. And I have a function here, add vector to vector. Just remember some of our gradients we had to use addition of the gradients, or just adding a vector to a vector or an array to an array. Here we have a function multiply a matrix times a vector, and all of these matrix multiplication are all in my matrix.c code here. Little by little we go through until we end up getting the B1 gradients, the W1 gradients, and then we get our E gradients for our embedded gradients. And finally, we have to undo the embedding of the E gradients to get our C gradients. So all of this backward propagation, I have it all in backpass.c. That's all in here. And you can see all the functions I've written here. DL, dy, predicted, get B2 grads, gradients, get W2 gradients, get the bias gradients, get the gain gradients, get DH/DZ, get DL/DHN, get the B1 gradients, get the W1 gradients, get the C gradients. See, just moving backwards through the network. And then we do the update function here, which updates all of the tables. And if you look at the main again, where's main? After we go through all of that, then we do our update the weights and the biases. So these lines 221 all the way down to 227, we end up with updating all of those 7 tables. And after we update all those 7 tables, we have to free, because this, of course, we're managing our own memory here. And then we can, and then our loop basically finishes here. So our final loss after training. And then we can go and do the split loss. And remember the split loss, we divide the names, the original names into 3 groups. One group is used for training, which is 80% of the names. Then we have another group for development, which is 10% of the names. And we have a testing group that has 10% of the names. And then we can go into the testing function, which is down here. And the testing function consists of, well, remember I had to write this little special function here to convert floats into doubles. So I create a double array here, and I just copy the floats into the double array. So I give it the array of floats here, and I return an array of doubles. And I needed that for generating new names. The MakeMore function here, again, I'm using the GNU scientific library here to do my random number generation. And so how many names do I want to get? This count here is going to tell me how many names to generate. And I just go through here. This for loop tells me how many names I want to generate, and the while here will go through until I hit a break, when I hit a period to get out. So I got the end of a word. And again, I'm using here the GNU multinomial function. And I did that. I'm using, I tried to get the same names, but you notice I'm not getting the same names, and I'm not getting the same losses as I do with the Python program. If you look here, my very first loss, 4.31868, that's the same here, 4.31868. But as soon as I do 1,000 iterations, my loss is now 2.43, while the loss here is 2.40. So you can see the losses here at the end. The training loss is 2.06 for the Python program, and my training loss here is 2.12. So it's a little bit off. And then the development loss is 2.11 for the Python program. Mine is 2.15 for the C program. And my names, of course, are different than the names here in the Python program. Nevertheless, I think my names are probably just as valid as the names in the Python program. They look just as good. Anyway, So why do I get this difference? Well, I've narrowed down why I get this difference to one particular place in the Python program, and that is this the loss with respect to HO. So if I do this here, let me just put in HO dot under GRAD. I will just say that I want for this very first layer, I want to retain that as the gradients of that, because what I want to do is at the end here, let's see, where is it? In the backward pass, at the very first time, what I want to do is I want to look at what the loss is with respect to that first linear layer. So I can print that out. If I print HO dot gradient, but you know, that's going to be, the problem with this is going to be by the numbers I'm using, this is going to be 32 by 200. The batch size is 32 and the number of neurons I have are 200. So that's going to be a lot of data. So, but if you look at the formula for working out the B1 gradient, you know, if I look at B1, this guy here is basically just going to be, what was the B1 gradient? If I go to main, let's see, what did I have in here? Main, where did I have that? Oh, actually, I just look in here. I think it's just, I just should look in my parameters. Bias one is 200. So basically, this is just going to be, the B1 grade is going to be 200, because what it comes out to be, it's basically a summation, the sum of HO dot gradients. So what I can do here is I can do, instead of printing this out here, which is going to be a lot of information, too much information, I'll comment that guy out. And what I can do is I can print out like this. I can say print, oops, and I'll print torch dot sum, and what I'm going to do is I'm going to sum the HO gradients, and I'll sum them over 0, which is the columns. I'll sum each column, so I'll have 200 summations, and this summation here should end up being also 200, and it should end up being the same as B1 dot grad, or the B1 gradients, even though it's only one pass. And actually what I should do is stop it after that. So I'll just put quit here. I just want to stop it there, and let's see what those gradients come out to be. So I'll save that, Save all, and then what I'll do here is I'll just clear this guy out, and I'll just run that, and that'll just do one pass, and they'll show me those two outputs. So if I go here, then you can see this first one, this one is the summation of the HO gradients. There's 200 of them. And the second one is just B1 gradients. And you can see the B1 gradients are exactly the same as the summation of the HO gradients. You see 2.3, 2.3, like that. 3.725, 3.725. And if I go right to the last one here, 6.98492, 6.98. So you can see that this line here, 105, is exactly identical to 106, which tells me that if I go to the formula for working out the B1 gradients, it's basically the summation of all the columns in the HO gradients. The problem is that when I do this myself in C, my HO gradients are identical to the Python HO gradients, but my B1 gradients are different because the summation, the way the torch sum function works, is unique. The way it does the summation is, to me, it's unknown. I have scoured the whole web trying to find out exactly how Torch does the summation, and I couldn't really find a good answer to that. So that's why my numbers are different. So just to put that in writing, let me put that in writing this way. I'll say it like this. I'll say I have B1 gradients are equal to the sum of the HO gradients. Basically, that's what it is. Now, so my C HO gradients are identical to the Python HO gradients, but my summation of the HO gradients, my summation of the HO gradients differs from the Python summation. So that means that ends up that my B1 gradients are different from the Python. And I can't figure out why my summation is different. So what I've done here is to show you, let me move that aside here. If I go to matrix, let's see, let me go to matrix here. In my matrix, I tried all kinds of summations here. Like, for example, I've tried, this is my main summing columns. I have an array here of M with rows and columns. They're all floats. And I want to sum them up. So what I do is because this is an array, I get a column. I get one column. And then what I do is I want to sum that column up. And I just want to return uh, the summation of all the columns. I want to sum the column one at a time and then return a vector. So this should return basically, if I give it M is my HO, loss with respect to HO, then it should return B1. It should return the loss with respect to B1. So some of the different functions I use to sum a column, I use this sum Kahan method. I've used this variation on the Kahan method. I tried to just convert everything to integers and sum everything as integers. And the last one I tried, well, I don't have it here. I also tried just adding them all up in C, just adding up all the floats, like you do in, your very first your very first course of programming, where you add up a bunch of numbers. You just go through and add them all up. Total equals total plus X. But that didn't work either. What I found that works the best for me is this pairwise summation. And if you look at pairwise summation, this is what's used by NumPy. What it does is it sums two numbers at a time. So it sums the first and second, then the third and fourth, then the fifth and sixth, and so on. And it's a recursive little algorithm that ends up with the sum of a column. So this array here is a column. There's the start and the end of the column, and it just returns here the sum of that column. And so when I take this array here, HO.grad, which is 32 by 200, if I was to put it through NumPy summation, it also gives me a different answer. It doesn't give me the same answer. So what it boils down to is that this sum function, this torch sum function, how it works to me is completely unknown, and I can't seem to find an answer to that. So if anybody does know what the answer is, or how exactly that sum function works, I would appreciate it. One last thing I tried on that sum function was I even tried to reduce the array, for example, to an echelon, row echelon type array. I thought maybe that's what they're doing, is some kind of trick to reduce the array in some way to some echelon form. But that didn't work for me either. Like, I spent way too much time trying to understand how that sum function works, and I never really got anywhere. So anyway, for what it's worth, I think my program is pretty good. It's not 100%. The names I get are not too shabby. The results I get for my loss, not too shabby. Things seems to work okay. So I think I'm going to end it here with, what will I say here? I think I have a little review here for batch normalization. It works by normalizing the output of a previous activation layer by subtracting the batch mean and dividing by the batch standard deviation. It's used to make training of artificial neural networks faster and more stable. But, and here's the weird part, reasons behind its effectiveness remain under discussion. I got that from Wikipedia. So apparently, people all agree that batch norm seems to work. It makes training easier and faster and more stable, but nobody can quite put their finger on why it does it or how it does it, or I guess just why it seems to work that way. Okay, so I'm going to leave you with that. My final comments are that Andrej Karpathy's videos, I think, are fantastic. The guy is a great teacher. I encourage all of you to watch all of his videos. I certainly learned a lot. Maybe just enough so I can talk a little bit about artificial intelligence. I guess that's probably a bad word. Better word would be maybe machine learning or neural networks. A lot of the terminology I've learned. I learned a little bit of Python along the way. I've refreshed a lot of my basic calculus from my college days, so I enjoyed doing this, and I hope you enjoyed watching these videos. So thank you very much, and keep programming.